Hello everyone. So in this video of the 5 transistor OTA series, we will discuss the large signal analysis. Till the previous video, we have calculated the noise offset and other related calculation for cascode structures also that we call the telescopic op-amp also. So in this video again on the 5 transistor OTA, we will see how it will behave for this large variation in the signals at the gate of the input pair, and the same concept will extend further for the slew rate calculation. Okay, so how we will proceed? So this tail current source contains a 2 I node current that we know. Just I should mark some numbers here, which will be more easy to relate, or later I will mark the numbers for the VDD, what is the VB naught value, and what is the common mode of input. So one thing that I assume here is this V in one is my some common mode. On top of that, some DC signal that I call the VDC, and V in two is my common mode signal only. Okay, so one side, both the sides have a common mode applied, and the input first input I am changing, or I am sweeping with a VDC input. So what will happen? We will see. So actually, we want to see V in one minus V in two versus what do you call I out. That is your this is my output terminal. So it will be a I out. Okay, and V in one minus V in two versus V out. So we will see this thing. So we'll see this thing step by step. So what will happen actually? What about this node X? So this I call the node Bx, or better to say this node X. The potential of that is Bx. Okay, so this node is a X. Let call this node Y. Okay, and this is out. So this we know this is my out node out. So with this variation in the input from very starting to this large value, so called this VDD. So what I will do here, let's suppose VCM is my VDD by 2 signal. Okay, not a signal. It is some common mode which is a VDD by 2 midpoint of this supply to ground. Okay, and so what is my VDC? I will vary my VDC from 0 to recall, yeah, 0 to VDD by 2. So what exactly we will see that from this conclusion, what we will see that my input one is actually varying from VCM to VCM plus VDD by 2. Actually, it is varying from here. And what about my input 2? It is the constant at VCM. Constant at VCM. Okay. So what will happen when both the inputs are same, that is a common mode VCM, then the current is expected to flow is equal. So the current ID1 for both inputs common mode for both input 2 equal to for both inputs equal to VCM, or current is expected ID1 equal to ID2 equal to I naught. Okay, if this 2 I naught is flowing through the M naught. So if there is some change in the input side, if V in 1 is changing, what will happen? Ideally expected that ID1 should increase, and what should happen? ID2 should decrease, so that my ID3 is constant. ID naught is constant. So my ID naught is constant. Okay, this is 2 I naught. Okay, fine, but I'll call it as id not also, the id not. Okay, so how this is constant? It is actually controlled by this vv naught, which is my external biasing. Vv naught is control voltage, controlled or not controlled, it is my controlling voltage. Okay, so what is it? It is a, so vv naught is a controlling voltage. So what we will call the m naught is as a voltage controlled current source. This is my m naught. Okay, so whatever current flowing through the m naught is just a tail current, so it is a fixed current, that we all know. It is a fixed current. So one thing we know well, if one side of the input is increasing, the current will increase on that side and the current will decrease on the other side, because what we are ultimately doing, the current is increasing this side, it directly means current is reducing this side. So what can be seen, at one point the complete current will flow through this m1 side, hence the m2 side is completely off. So this output current is totally current, which is nothing but 2 I naught, which is ID naught, completely flowing through this side M1, M3 and M4. So M2 is totally off. So this is going to see. How it will happen, we will see. So biasing is already told in previous video. So VV naught is biased voltage. So this node X is such that my lower transistor is in saturation. So this need not to explain again. Vx is, so this thing I am telling for good design. But on large scale, we will see that transistor will leave their original state, because we are sweeping this input without any control. So this is my V in one. This is the V in two. So okay, what is exactly happening here? Okay, so we will see here. Actually, this input, which is consist of VCM plus some DC value on top of that. This is the VCM. So I'll say my VDC is varying from, that I should say, minus VDD by 2 to plus VDD by 2. So I have checked the results for this particular. In previous video I told you, sorry, in previous slide I told you to vary it from 0 to VDD by 2. Okay, so actually it is not 0, it is minus VDD by 2. We want to see some symmetry in the structure, so we are taking some symmetric variation, which is a minus VDD by 2 plus VDD by 2. Okay, so what it will happen here, it will like okay, minus VDD, so VCM is VDD, so it is a minus VCM minus VDD2. Okay, sorry, this is a VCM plus VDD, so it will vary from VCM minus VDD by 2 to plus VDD by 2. Okay, yeah, yes. So what is going to happen, as I know that VCM is VDD by 2, so actual my V in 1 will see what it will vary from like VCM minus VDD by 2 means it will vary from 0 to VCM plus VDD by 2 means VDD, because VCM is VDD by 2. So this is the total variation of V input 1, and input 2 is constant, which is VCM. Okay, so what will happen at this node, and what will happen at this node called Y, call out, and what will happen at X node. So as this side is increasing, so first of all, let us start at the DC of minus VDD by 2. At that time, this is 0. So gate of transistor M1 is 0, means it is off. So the total current is flowing through the M2. It means whatever the output current, it is nothing but the total 2 I naught, which is flowing through M2 side, not from the M1 side. So one thing that I can consider here, this voltage, when this voltage or v in 1 is nearly 0, because vcm minus vdd by 2 means it is 0, then this voltage is also 0. As we will increase this V in 1 from 0 onward, what we will see, increasing V in 1 directly means we are just increasing VDC. Okay, so this is the only point which is the only voltage which I am increasing from minus VDD by 2 to plus VDD. So when it is minus VDD by 2, my input 1 is 0. It means M1 transistor is off. So it means the current is also off. No, there is no current, because this node Vx is also nearly 0. So the current I3 is not also existing, sorry, not I0 is also not existing. So what I'll draw this variation scale of VDC, which is minus VDD by 2 plus VDD by 2. Okay, so what is happening, as we can see, I0 and Vx. Okay, so let assume every one of you know this thing. If both the inputs are equal, and this voltage I call the common mode, and this is enough so that M1 M2 both are in saturation, M0 is also in saturation, everything is fine, then what you'll see, Vx has some value. If both the inputs are going low, means Vx is also going low. If any of the input is going low, Vx is also going low, but this variation is small. So what I can see, when my V in 1 is near or exactly 0, because my VDC is minus VDD by 2, this Vx is also 0. So this Vx is also 0. As we will increase this V in 1, it will start increasing. So what I will see here, it is something like, my Vx is something like this. After that, it is increasing linearly. Okay, so somewhere here it is less than VDD, but it is some value. It has some value which is near less than VDD. So yeah, it is means somewhere here it is going to non-zero. So till this point we can see nearly the current is also means yeah, already VB naught is applied, so this transistor is on, but this VDS is very less, or I can say the current that flows is also too small. So this is observed by some like mean of implementation. So you will see the current is something like this. This is the current profile for this I naught. Okay, you can see and simulate also. So what is exactly happening, my Vx was also 0 when my V in 1 is 0. So it will increase, and after that increase in the V in 1, this Vx is also increasing linearly, or somehow near linearly. And this current which was previously 0, I naught nearly 0, it is now also increasing. So what happened with the ID1 and ID2? So I'll also mention here ID1 and ID2. ID1 and ID2. Okay. So with this we'll see this current ID1 and ID2 is also increasing. Current ID1, it is also like going like this. Somewhere here it is something. Wait. Something missing. So it is also increasing. So after this point it is going like this and combining this. And what about I2, which is also increasing? ID2, it is also increasing somewhere here, and after that it is coming to this. Okay, so something is happening like this. So near this 0 of the VDC means here what we will see, this V in 1 equal to V in 2 equal to common mode. The graph is not exactly, I think I'm not able to draw it correctly by hand. We will show this thing. I will show this thing in simulation background also. Okay. So what is happening at this point? This ID1 equal to ID2 equal to I0. Okay. and after that they will split, and this will touch this complete current, and this will go to nearly zero. But in this some particular reason, you will see up to some point these currents are means both are non-zero, because we directly cannot say that if my V in one is just going above this VCM and V in two held at the VCM, the current is not directly going to switch completely through this M1. It will slowly increase, and then this complete current will start flowing through M1. Okay, so it is not going to directly happen. So you can see from the profile. Now we'll see this variation of the Vx, which I told you it is a linear, looking like a linear. And what about the node Vx and Vout? When we see the node Vx and Vout, we can see this node Vout actually. So in node what he said Vy, it is actually changing very less over this range of minus VDD by 2 to plus VDD by 2, because what we will see here, what is the Vy value actually. Okay, so what about this node Yx? So first we have to tell who is deciding the node value. So who is deciding? We can see whatever the current flowing across this, if this transistor is well in the region of saturation, just I'm telling about the region of saturation, then you can say there is particular relation for that VGS. So what is this VGS? VGS of, let I call M3, it is M3, it is M4. Now what we can see, this is something which is nothing but the current 2ID1 by nu PCS W by L plus VTHP of 3. Okay, so this is the voltage. So what we'll see, this node Vy is VDD minus, what do you call it? VDD minus Vy. Sorry, VGS 3. So as we can see, this dependence of this voltage VGS 3, which is nothing but, if this is in saturation region, then only I am telling. Other relation you can also find. It is like a proportional to root of ID3. So this means variation in ID1 is deciding what my Vy is. So this variation is not that much. Hence, this Vy variation is also less. Vy variation is also less. And what about this out node? This out node, we can see it is a high impedance node. One thing. One more thing that I should say, it is a low impedance node. Low impedance node. And this is my, yeah. So, whatever the current is changing across this transistor M2, which is like the ID2, in particular reason, when this these both the inputs are equal, that is called the common mode value, whatever we decide is VDD by 2. These currents are equal, and any perturbation around that point, any change in voltage input difference around that point, we are seeing that the output node is influenced much. So there only we decide the gain. So from here, just you will be clear here. So what we are seeing, from minus VDD by 2 to plus VDD by 2 of my VDC, what we can see, this Vx node, oh sorry, not Vx, Vy node is some here, and it is going slightly lesser and nearly something like this. So this is my zero, and this potential, let I call it is minus of, means few millivolt minus del V, and this is some plus del V area. So overall this is very small, and in this region, or I call it few millivolts. In this few millivolt region, we can see this Vy is not changing much, because it is controlled by the current, or every voltage is controlled by the current overall. But this is a low impedance node. From the gain point of view, we also can see, let's see this variation of Vy from gain point of view. Let this is my structure, and this is the first input, and let's suppose this is some value. Let's say node is shorted, and what we see from gain point of view also we can see this Vy node. If we are in a well operated region of saturation, then what we'll see, what exactly this del Vy by del in1, which is called the gain of this node, what it is. It is gm of, let this called 1, this called 3. What it is, gm of 1 divided by gm of 3. That's it, no? So it is a small gain from a small signal point of view, from a small signal point of view. Also, this thing can be seen from the large signal point of view also. When we are varying this signal, I can see in this particular regime of this 2 del V, you can see this variation is not much. It is small variation. Okay, so gain is less. Now, what about this output variation? We will see as my Vx was increasing slowly, like something like this was the Vx somewhere here. At here, Vx is some value, which I'll call it is somewhere near less than some value of Vdd by 2. How much it is less, we'll tell. Let before that I should complete this part. Okay, so what is the output variation that I should tell first, and how it looks like? So output is going like something like this, and after that is a huge increase. So then there's something reaching like VDD. So in this region, we'll see there's a large slope in this particular region. This large slope in this region indicates in this region large slope in the region around V common mode region, indication of, it is an indication of large gain. So this thing we can see both from small signal and large signal point of view. So yes, so this is the variation of the output signal. This is my V out. Okay, so this is my the Vx variation. This is the V out variation, and current variations I already mentioned in the previous page. So what we will see from here, this what is the value of my Vx node at input equal to both the inputs are equal. So Vx value when both the inputs are equal. So in general, what happens? I'm just making this rough diagram. What it is? It is nothing but at that point, what is happening? This is my I naught. This is the I naught, and this is 2 I naught. So this is X node. What is actually happening? Yeah, when both the inputs are common mode, the currents are equal. Then this value is what? What is Vx? Vx is actually nothing but V in 1 comma 2, any of them, minus Vgs of 1 comma 2. Okay. Anyway, I have this you can see. So actually, my this Vx is less than V divided 2. I mean to say this Vx is 1 Vgs less than the common mode value. So this thing we can see. So this is the case when common mode equal to, VDD by 2, input 1 equal to input 2 equal to common mode. Okay, so any of this node voltage or any of the side increases, this Vx is also increasing, but the increment in Vx is assume small. Not we are assuming small, but I can say this current is suppose increased by some del I value, and this current is reduced by some del I value. So if I am assuming the both the transistor, if we are around, if we are around the if we are around the common mode value, Cm value, then what you can say, we are assuming both the transistor in saturation. Assume both M1, M2 are in saturation. Just from the analysis point of view, I am just taking that small reason. What we can say, if my ID1 is increasing, ID1 is just going to I naught plus del I, and ID2 is going to I naught minus del I. So what is happening with VGS1? What is happening with VGS2? So if they are in saturation, we know the relation, we know one relation, that is nothing but VGS is what? This is 2ID1, some constant term, WIL, VTH. So everything is constant. If ID1 is increasing, then what we should say, this VGS1 should increase. If VGS1 is increasing, now point is coming. If VGS1 is increasing and V in 1 is also increasing, then why Vx is increasing? The point is that why it is increasing. We can see one thing here. If we are increasing input V in 1, and if we are this is we are increasing externally, and if we look at the effect due to increase in V in 1, I D1 is increasing. If we are looking at the effect, this is the cause. V in 1 increment externally is a cause, and if we are looking at the effect, what you see, this is also increasing, but this increment is small. It is smaller than V in 1 increment. That you have to figure out. Hence, we can see that Vx is also increasing. Hence, we can say Vx is also increasing because there are two quantities. That relation is very clear, that everyone of knows from mathematics. If my V in 1 is what? VGS1, um, okay, plus Vx, yeah. It is something like this. So if I am saying that my V in 1 is increasing, if I am saying that my V in 1 is increasing, VGA1 is increasing, and it should be constant. But point is not like that. If we are increasing V in 1, it is also expected increasing, but it is also increasing. So what we are seeing that it is small increment. It is small increment because dependence of current on this, the dependence of this voltage on current is some proportionality root of the current, not exact. So this increment is less. So to consider this point, this to consider this viewpoint, just to tell you about this how these nodes are varying when we are changing the input nodes. According to that, we can analyze, and on the large scale, we can see what is happening here and which is the reason where we exactly getting the gain. Okay, so in general, you can see what is happening. The other large signal, yeah, this is what I am doing. I am just varying one input and keeping other constant. If let we are increasing both the inputs, then what will happen? If we are just increasing both the inputs, just I am drawing the input pair. So other thing on the large scale we can see here, if we are increasing both the inputs simultaneously, what I should first define, V in 1 is my VCM plus VDC, V in 2 is again VCM plus VDC. Just I am defining the two inputs. So you can also vary from this zero value. But what I am doing actually, I am just taking like this, and I am varying this VDC amount, which is from minus means what I should say, minus VDD by 2 to plus VDD by 2, and keeping VCM as VDD by 2. So overall what is happening? V in 1 is varying from 0 to VDD, hence V in 2 also varying similarly. So what we can see, when both the inputs are too low, This is also 0. Node X is also 0. Current is nearly 0. So these currents are also 0. So as we are increasing, these currents are increasing, and this I naught is also increasing. And I naught is increasing, these currents are increasing at certain value. We can see what is happening here. Okay, on the graphical scale, what is happening? If this is current ID of 1, 2, and ID of tail current source. What is this? This is my VDC. Okay, so this is minus VDD by 2. This is plus VDD by 2. Yeah, both the inputs are increasing. So this is a point where a common mode is there. Yeah, when VDC is 0, common mode is there. What we can see here, this node Vx is also increasing the same way, but this time there is a difference. It is going slightly higher than the previous value, because this it was also increasing in the previous case, but because we were only changing the first input, the input one, so it was here it was same, but it was something like this. Okay, so it was when only V in one was changing, only V in one was increasing. Either both the inputs are both the inputs increasing, both the inputs are increasing. Okay, so we can see this difference. And what are the other things you can see? This current, both the currents are always equal, and they are somewhere here. And after that, you will see this I naught is going somewhere here, sum of these two. So this is my I naught. So what is happening after, still we are increasing, and this transistor, for the transistor M1 and M2 will go out of the saturation. We know if we are increasing this common mode much out of the range, then we will see what is the nature of this current. Okay, so yeah, output nodes we can see they are not like output Y is something like same. It is somewhere here, so it is also not changing much. This is my output Y, this I call output Y, and yeah, this is the Y, and this is the out node, and out node has a strong slope here. Also, again, it is strong slope here. Just you can simulate this thing if you have this tool, simulated ones. So these are the two types of large signal variations possible. You can see what is the current, how it is changing, and what is the output exactly changing. Okay, so I have just a waveform that I have taken. So here I have seen this. This is my total current. This is the tail current, and what I'm seeing here, this is my minus 2.5 volt VDC. It is a minus VDD by, or this side is a plus 2.5, and it is a VDC as 0. Okay, VDC is 0. So we can clearly see somewhere here, and both the currents are equal initially. Yeah, this is the slope difference. So my VDC is also increasing like this. This is my VDC curve, and when both the inputs increase, it going like somewhere upper value, somewhere up. And when only this is increasing, only input one is increasing, you can see it is going slightly lesser. It is going slightly lesser. So this is the Vx variation, and what we see in this particular regime, this is like a small variation around this common mode. When both the inputs are equal to common mode, the currents are equal, and after that you will see this is my ID1, this is my ID2. Okay, so after this point ID2 goes low, ID1 goes high, and you can see the strong slope. This is the strong slope for this output. This is my actual output. This is a strong slope in this region. Okay, so if you want to calculate the gain, or you want to see the gain, we have to see in this regime only. In this region, we will see this gain, and rest this tail current is nothing but I tail, that I should say. I tail is equal to ID1 plus id2 always from the KCL at this lower node. So you can see from here the variations are there. So yeah, the one more thing, this is my v y. So what we are seeing here around this minus 2.5, or it is around minus VDD by 2, because my VDD was, I will write here, my VDD was 5 volt here. So VDD by 2 means 2.5. This is nothing but a variation of VDC from minus 2.5 to plus 2.5 volt. Okay. So from here I can see this is around 4.67. So it is near VDD. So this much headroom, this much room is there. VX is near VDD, and what we can see here in this region, a small region around this common mode, you can see there is only small deviation in this VX. So from this point of view, we can see there is a small variation. So Vy is changing less. Del of y small is small, so means gain at too small. That's why we can also see from this small segment, that's why we say that the entire output that is of our use is on this output node only. This v y node is of no use, so we cannot compute the gain here. But in the differential structures, total or complete differential structures, that node is equally important, because there also we get some gain. But in this case, what amount of the voltage we are getting there is very small. So overall, we are considering the single-ended output. So what we are seeing, these are two inputs and single-ended output. So one end is what? We are just reflecting its effect on this right side. So yeah, this is the output node. Some node that was my Y node is also there, but it is not utilized in the gain V1, V2. Okay. So this is the scenario. You can do much more analysis here. Yeah, from the homework point of view, what you can see, you can take one thing that you can take from here for the homework purpose. What you can do, take one complete differential structure that I will call as RD, and do this analysis again, large signal analysis, complete differential structure, and do the same analysis here, and also notice what is happening at these nodes Y and node out. So what is happening here? This I will call node Y. This I will call node out. So this is the complete differential structure. Okay. So we can see that how these currents, which I call as ID1, ID2, what is the variation at node Vx? We have to see the plots. See the plots for two types of variation. One, only one input is varied around this common mode, is varied around the common mode, around the common mode, and other is fixed at common mode that we have done, and second is vary both the inputs. Okay, so in the coming video what you will see, the 5 transistor OTA response for the step signal. Okay, so this is enough for this. Okay, so it is enough for this video. We will see other uh, things in this 5 transistor OTA structure, which are nothing but slew rate calculation, analysis for the step input, which I call the transient analysis, and also the frequency analysis is the remaining part. Okay, so this is enough for this video. Thank you.